Okay, in our last three videos, the 5 kW, the 8 kW, and the 10 kW, we went over different ways to wire them up, going over the anatomy, and we eventually matured to the safety end of it on the third video, which in the order they went was 5K, 8K, then 10K. On that 10 kW, it was very similar to the 8K, so we didn't have to go in depth and be very redundant on that information. We more covered some of the safeties and making sure that that blower was going to come on. This video is just very specific on safeties. I know your time is valuable, but like I said, we're in this together, so I'm trying to teach you. That's my goal, is to reach out to you and help you simply understand this, so when you're in the field, you can make better sense of it. And then you're watching this video, obviously your time's valuable, but you want to get as much out of it as possible. So typical person to watch this video might be somebody more experienced, and they would most likely get more out of it. Somebody on a junior level of that experience level, they may not get as much out of it, but you know, we have to level up. So I think this is a mature video for everybody. We're dealing with single phase here. Just quickly go over the diagram that I have. It's pretty much left over from the 10 kW, 8K, and 5K. You know, we have fusible links. That stands for the FL. And we have limit switches. That stands for the limit switch, LS. These devices that I drew up here, because there's no legend, just to quickly go over it. We're using these squares with the circles in them as lugs as my line voltage comes in, L1 and L2. Anytime you see the circle with no color on it, as you can look at the outer circle here, the same on this side here, that's the ceramic piece, because we obviously don't want to be drilling a hole through our metal plate, sending a bolt through it, putting power on it, then the whole plate's energized. That's never going to work. So we have to use ceramic pieces. They can handle the heat. At the end of the day, there's a lot of ceramic pieces on these heat strips. One thing you want to take into consideration is how you handle them. Not just for the ceramic pieces being able to crack or break, which would make those heat strips inoperable, because they would not be safe. But also make sure that you're careful with the elements themselves. And so you don't want to, as you're sliding these in the cabinet, catch anything metal and, you know, push too hard and not realize that you're hung up, and then next thing you know, you're going to stretch these springs out, these coils out. That's going to change resistance. If any of these elements touch, it's going to overheat in that area, and that's going to cause a defect. So you got to make sure you have proper spacing. And if you look at this, you know, it's passing through many different sections with ceramic pieces, and it's not, this is actually a good quality set of heat strips, believe it or not. If you look at how the spring weaves in and out, and if you look at how many ceramic pieces there are and how much metal there is that's holding the ceramic pieces, you know, you got to think about it. You know, there's not a whole lot of slack in this. There are some heaters that have a lot of slack that kind of naturally hang down a little bit. We'll call it what it is. They're obviously cheaper heat strips. Those heat strips are most likely going to have a problem, especially if you start catching on metal when you're sliding them in and out. That doesn't mean that you can handle these roughly, because they're, you know, the integrity of them's better. Still be careful with that. So enough of that. We want to make sure that we understand that there's two legs of power here. We color coded them. So on the board you'll see black and red. My wires coming in, my line voltage coming in is black and red for L2 and L1. We want to follow that color so we don't hit two legs of power, because that's very dangerous. and that's going to affect the entire house if that breaker does not trip. It could even affect the transformer on the power line if the main breaker doesn't trip on the panel. So you got to be thinking about all of this as, let me slow down a little bit, let me not bypass anything, let me handle it as carefully as possible, and let me make sure that I don't have two different legs getting too close together and causing that those legs to butt. This can be 8 kW, this can be 10 kW, doesn't matter. This just represents I have two strips. You know, I can dumb this down and delete some of this stuff and just knock it down to one strip, but you know, there's really no fun in that. We're trying to get as much out of this as possible. So we're starting off with safeties that are on the high voltage side only. I'm going to go ahead and put a relay on here, and I'm just going to wire this up, and then I'm going to delete some of these limit switches on this side, and I'm going to show you that if I put just a limit switch on this plate with the relay, how I can utilize that limit switch to break the low voltage side. So right now we're breaking the high voltage side. I don't have to do it that way, but the way these strips come, okay, they have it that way. So I want you to look at this for a second here. I have fusible links on one side. I'm going to pass high voltage across these fusible links. And providing that these links are closed, right? As you noticed in our last video, it's open on the top side, closed on the bottom side, right? I'm going to have power on the other terminal, the other device. At that point, I can take power out of here and I can energize one side of my heat strip, okay? Which would provide line voltage from one leg. The second leg of power, typically I'm going to break it across the relay, and I have a choice that I can come up and hit the limit switch. Providing the limit switch is closed, I can come out of the limit switch and then energize the other side of the heat strip, energizing that one set of strips, and do the same thing on the top side. Or what I can do is I can actually run low voltage in here, out of here, in here, out of here, daisy chain them, run it back to my relay, and I can just break across the top side and the middle section on my 2-pole thermal disk time delay relay, my sequencer, and I can just come up once it's broken and I can energize the left side of my heat strips all the same. However you want to do it. So there's not necessarily a right or wrong way in that scenario, okay? How we're going to do it on my diagram is I'm going to go ahead and wire it up on the high voltage side, and then I'll separate it and show you what it looks like on the low voltage side. All right, so these limit switches, they open at 165 degrees Fahrenheit. They close at 40 degrees Fahrenheit. And so typically when the blower's running, you know, we're not going to achieve 165 degree plenum where these heat strips are right above that. We're not going to achieve that kind of temperature. We're probably running between 90 to 120, maybe 130 degrees. So a lot of wiggle room there. However, if we're not pushing enough air because the filter's completely restricted, along with a clogged up evaporator coil, and I'm saying the motor's running and it's not turning at its full RPMs, a lot of resistance there, you may find these limit switches kicking out. That doesn't mean you have a bad heat strip, that just means the limit switch is doing its job. And so that's very important to think of that. So you want to do a full inspection if your heat strips aren't running. You want to still make sure that you have good air exchange, just like you would on the coil. You gotta make sure you have good air exchange on the coil. You gotta make sure you have good air exchange on these heating elements. And that's what those limit switches are there for. So we're gonna go ahead and move. I'm gonna go ahead and take the 2-pole sequencer. We'll go ahead and put it over here. We'll go ahead and wire it up. Let's go ahead and do my L1 first. Simple. We're going to come out and we're going to land on our fusible links, and that side's already done. That quick, pretty simple. We're going to go ahead and do the L2 side. We're going to come in and we're going to land on the top and bottom side of the relay. Now, when I say bottom side of the relay, I'm not talking about your low voltage side. I'm talking about the middle section here and the top section here, right? Pole 1, pole 2. So right now, this is a normally open position. What we want to do is land it on our limit switches. And as long as all of our safeties are closed and the relay is energized, meaning that it's closed, heating elements will run. And that's great. Lots of safeties here. But how do we know that, we're not going to cause a problem with this design if our blower stops running, right? And that's what we have to start looking at. So we're going to go ahead and dive into that here. Matter of fact, we'll go ahead and just take a 9380 relay. I'm going to go ahead and put it right here. Kind of like before, on my 10 kW video, you'll see that I put 2 of them there, and I wound up wiring up my blower motor, and I used a W2 and I used a G call, and I made sure that if I was calling for heat, I would run my blower. I'm going to show you how to do this another way with using one relay. And the reason why is because when you wind up converting these motors from modules, X13 modules, to PSCs, just a truck stock version, get your client up and running, or if you're working on an older unit that just has this and you have to do a little bit of surgery on the high voltage side of the controls, you want to make sure that you understand how to use your normally open, your normally closed terminal to benefit the situation with the motor running in excess with the heat strips being on. Alright, so we're going to go ahead and write some low voltage up here. We're going to say red, common. We're going to say G for fan, and we're going to use purple because white doesn't show up as W2. So as you already know, I'm sure, if not, you do now, common on the low voltage side of the relays. We're going to go ahead and run one up our other relay too while we're at it. We're going to come over and do fan. That's going to come over and land onto the bottom side of the 9380 relay. I'm going to hold that up for a second so you understand. This is the relay we're talking about, so this would be your coil. We're going to do other videos that better express relays and their practical applications. For this video, we're trying to stick with the heat strip content so we don't overwhelm you and have a 5-hour video and still no air conditioning when we're done. Alright, so we're going to go ahead and do the high voltage side of this. Bear with me. At this point, I'm not going to draw L1 and L2 on the motor. I'm not going to do that because I did that on the 10 kW video, and when I did that, the board looked pretty sloppy, and the last thing I want to do is confuse you because that would defeat the entire purpose. So we're just going to assume that the other leg of power is present at all times, and we're only breaking one leg of power like we have to toggle the motor on and off based on a G call. I think that's very fair. Now you notice here I have a red up here. You might be asking, how come he drew it up there and how come he doesn't use it? Because if I don't put it there, it may confuse you. As you can see, I don't need red to bring my fan motor on or my heat strip on, because what's going on is red's going to my thermostat. All right, that's it. It goes to my T-stat, and my T-stat takes that red and it says, here you go, G. Here's 24 volts for you. Here you go, W2. Here's 24 volts for you. So I'm not going to sit here and draw a thermostat and talk about how, you know, it makes contact on temperature rise and temperature fall and all that, because again, that's not what this video is for. But I'm putting red there just so you can understand that we're dealing with 24 volts. You know, nothing screams more 24 volts than writing red and C up here, right? So looking at the W2, we're gonna make sure we're on purple. We're gonna come up, and there we go. And right now, if red through the thermostat energizes W2, the heat strips run. If red through the thermostat energizes G, the blower comes on. But as you know, a thermostat can easily make a mistake. If it faults, customer can put it on, you can put it on, anybody can there can be an error here. So what we want to do is we want to make sure that if we have power, okay, on this terminal that's breaking, all right, one leg on this motor, I'm just going to call it common, okay? We want to make sure that we can still get power here in the event that this relay is stuck or the heat strips are calling and my blower's not calling, okay? And so if we were to do that, simply we would take and we would come off of this terminal here, which is normally open. So I'm going to go ahead and use white so we can kind of see this a little bit. We're going to say this top part is normally open, this bottom part is normally closed. What we're referring to is the top side of the relay being normally open, the bottom side of the relay on the contact side being normally closed. And all we have to do is just jump this to here. That's it. Just simply jump it to here. Now what we're going to do is, and it's not foolproof, but nothing really ever is. If it was, I don't think there would be as much work for us, right? If I stick on the middle section, or if I stick on the upper section, okay, and the other one is not stuck, I have to hope that, you know, any, mini, money, mo, which one, 50% or the other, is going to energize and backfeed power to my common terminal to run my motor. So I don't like this setup, but it is one way to do. So it's a 50-50 shot. I'm going to come off the top side. Most of the time when these relays hang up, believe it or not, it seems to be on the top side. I see it on the bottom side too, so don't think that it can't happen there. But all we're going to do is we're going to come over here and we're going to just send power back up. It's as simple as that. Is it foolproof? No, it is another way of doing that. And so now how do we know that we're not going to backfeed power and energize the heat strips? Well, it's simple. Because if I'm not getting 24 volts for the call for fan, okay, then this is normally closed, right? Well, if I'm not supposed to get a call for W2 anyways, if I'm not getting a call for W2, well, then I'm supposed to be open over here. But in the event that I am closed because the relay's stuck, then at least there's always power on this terminal. And without having power on my low voltage side, the G, then if I have power here, then I have power here, which gives me power here, which allows my motor to run. Now, like I said, if I'm going to the top terminal here and my middle terminal sticks, I have to rely on my limit switch fully in this application. Unfortunately, it is the way it is. What I like is, you know, when we're using different types of safeties, we're allowed to make a difference on this situation here. So let's do this. I'm going to go ahead and take, actually, you know what? Let me undo some of this. Okay. All right, so the traditional way that it's wired up. If I took the current relay, I don't know if you guys are familiar with a current relay. Basically, what a current relay is it senses an amp draw. It has a normally open set of contacts. I'm going to enlarge this so you can get a better idea, because I don't have one here to really demonstrate. Give me a second here. Okay. I'm going to just keep my finger on it so we can better see. There we go. So I have a normally open set of contacts that will close if there's current going through this. So I can take this and put it on L1 or L2, let it run through there, just clamp it on there. This is obviously a Johnson Controls product. I can set my ampacity to whatever level. It says output closes over 70%, so I have to keep that in mind. And it can max sense over 200. So you can use this for commercial applications. Basically, what that means, and it does AC or DC. Really neat, right? So looking at that, my current for my output can only go up to 1 amp. So you got to keep that in mind. Shouldn't be a problem because we're not going to pull that much ampacity on that coil. So if I were to use something like this and put it, let's just say I put it over here and sensed my amp draw on, say, L2, then no matter what side of my heat strips, top or bottom, okay, no matter which string was energized, in the event that my relay stuck closed or called without the call for G, then this would sense that ampacity. And I can simply just pigtail, G right onto that relay. So let's look at that for a second. I can come up and say, you know what, I'm going to send power in, and then I'm going to send power back out over to here. That's another way of doing that as well. But that's probably not going to be on your truck. Not to mention it's an expensive part, and you'd have to retail it for something. So, you have to get creative here. There's other ways of doing your safeties, and you just have to continue to challenge yourself on what's going to be best for the customer and what's on my truck, what's going to make sense to the homeowner, what price are we going to be at. So you gotta sit there and analyze all these different scenarios as quickly as possible, so you can do what's right and do the best to your ability. But this is just to demonstrate that there are many applications for this. Even if you don't fully understand everything I'm showing you, it's just really good for you to get out of this that, hey, you know what, at least I know there's other ways. Let's look at another safety. I'm going to move the current relay back down here, and we can sit here and take this contactor. Now, the reason why this contactor looks a little funky is because I took a picture of it, and then how I took a picture of it, the piece of paper is obviously not as wide as this board. This is actually the contactor that I used. This is a 3-pole contactor. Obviously in this, I'm only need to break 2 legs of power. But what's nice about this is this contactor offers safety. In the event that it's in the closed position, I can take the normally closed contacts down here, or here, whichever side. Pretty much put them in parallel, so either side works. And basically, that set of contacts over here could energize my G. So if you see, I've got a common terminal, and then I have a normally closed, and I have a normally open. And so I would wire it obviously to the normally open terminal in this situation. So when my contactor pulls in, it presses down. I don't know if you can see, there's a little red button there that just makes contact, pushes that in, and then that will close my normally open contact. And if I had G on one side, it'll send G all the way through, you know, and then that would energize that relay. So if I said I want to use this type of contactor, I could say, hey, you know what? In the event this contactor stuck in the closed position where it was actually making contact, it would pull in my relay down here, okay, and that would relay 24 volts over to my blower relay and allow my blower to run. It's just another way of looking at it. And then, you know, maybe that's what I want to do for a customer with a 3-phase blower. Maybe I want to use this type of contactor since I can break 3 legs. Or if I had you know, an extra leg of power just for the heat strip. Some customers in a residential house will have 3-phase. I have seen that, and they'll have single-phase blowers and 3 legs of power operating the heat strip. So, you know, whatever the application, as long as you understand the path of electricity, there's a lot you can do there, especially when we're dealing with safety. Okay, so I'm going to go ahead and shrink this. We'll move that back out of the way. Put it up here. All right, what else here? Let me go ahead and fix that. Okay, let me go ahead and move this 9380. We'll move it back over here, and we'll go ahead and use a 9340, because a lot of you like to use the 9340 relay, and we talked about whether it's the 9380 or the 9340. One of the things that we cannot do is put, you know, high ampacity through it, because if we put high ampacity through it, you know, we're going to wind up melting those points. We're going to wind up causing a problem with that being safe. So if I were to traditionally wire this up, right, we're going to have 1 leg of power come to the top side of the 9340, and then the common terminal on the blower motor will come to the far right side, typically terminal number 3. And what I'm talking about is the 9340 relay. Down here we have our coil voltage. Up on the top we have our high voltage. This is 1 pole, 1, 2, 3. And we have terminal 4, 5, and 6. That is the second pole. Now, beautiful thing about this relay, again, we're not trying to make the video about this, so we'll just go through it quickly, is it's double pole and it's double throw. Really nice. So a lot of people like to carry that because, you know, it's a relay that can really get you out of a jam. If I had to do a quick truck stop, these would be the only 2 relays that I carried. I would say, hey, contactor, 40 or 50 amp, and I would say a 9340 relay, because I can pretty much do everything with those 2, even if I'm not using all the terminals. So, finishing up the low voltage side, G would obviously go to one side of the relay, and then obviously we need common, right? And that would allow us to toggle that on and off, as long as we're getting 24 volts on G, while we get 24 volts on W2 through the thermostat. However, once again, that's not going to work out so well if this relay sticks. If this relay sticks, we need to make sure that we are taking the relay and energizing the normally closed side. All right, so basically we'll take the second leg of power, which I can just jump over. You got to pick one, middle or top. We'll just pick the one closest on the diagram. And I'm going to say, if M3 makes M4, because M3 and M4 are stuck in the closed position, then the terminal 4, right, contact 4 on this relay is now got power from L2. In the event that that happens, I can sit there and say that I want power from common on the motor to energize that contact. I mean, that's just another way of doing it. So now we can go back and check it. Let's just say I'm getting power on G, blower relay is energized. All right, if that's the case, then we will be energizing across 1 and 3. If we are not getting power on 3 and we are not getting power on W2, all right, then even though 4 and 5 are normally closed, okay, it's not going to run the motor simply because we are going to not have power on M4 because M3 didn't make M4 based on the relay not being energized or being stuck. So it is safe. And if you're thinking, oh my gosh, well, path of electricity means that L1 is present through the motor windings. For those that are a little bit more further ahead, yeah, M1 is present on these terminals. But guess what else? M1's also, or L1, excuse me, is also present over here. See? So we're not taking L1 and button with L2. And again, this is a little bit more confusing for those that are a little bit more advanced. You might go, aha, I got it, I'm gonna use it. Again, what I don't like about it is I have to pick one, either M2 or M4 contact on that sequencer. If M1 makes M2, and I don't get a call for G, whether M2 is stuck to M1 or it may down here on W2 and I didn't call for G, guess what? In this scenario, I don't have anything that's going to energize my common because it's only here. So that is unfortunate. It's very unfortunate. And could we sit there and jump out M2 and M4? Let's look at that for a second. If we were to jump out M2 and M4 on a thermal disk time delay relay, then we are also going to speed up the process of thermal disk. So if I were to say M4 jump to M2, and what happens is, yeah, I can do that, but then anytime M3 makes M4, well, M3 is now also making M2. So it just, like I said, no matter how you try to dice it up, it's never a perfect scenario, which is one of the main reasons why there are so many redundant safety measures inside our units and why it's so important, because even though there's a lot of redundancy here, it's never enough safety for every situation, right? So the last thing you want to do is bypass something to jump across something. That's just not good. I'm going to clean this up just a little bit, and we're going to go ahead and put our limit switch on the low voltage side so we can see what that looks like. I'm just going to rewire these heat strips as well. Why not? We all know it's real easy. Okay. Matter of fact, we'll leave the fusible links. We're going to go ahead and move this relay. Give me 1 second. There we go. All right. You gotta really play with this thing to get it to do what you want it to do. Any teachers out there, especially in the public school system or private school system that are using some of these bores or different models, they'll know how sensitive these are, and they're not always going to do exactly what you want them to do, which can be a little frustrating. Which is why I told you in some of my other videos, just be patient. We're in this together anyways. So, if I wanted to get rid of some of these limit switches, let's go ahead and erase that. Delete. Delete. All right. Just gonna get rid of some of these things. Since we don't need them anymore, because we're going to change our design up. There we go. All right. I'm going to simply wire this up. Okay. We'll say that that's going to land here. That's going to land here. And obviously, without a relay turning this thing off, that's completely energized. So yeah, there's what it looks like, completely energized, no relay, just running all the time. All right. So we're going to go ahead and put a relay in there. And it doesn't matter which side I break. I can break the fusible link side, or I can break the side with no safeties. For simplicity, I'm just going to go ahead and take a contactor, and we'll put a contactor over here. There we go. And we're going to go ahead and just pigtail off of L2, come back over, and then we're going to just go straight over to our fusible links, and that's it. So now we're in action again. Pretty simple. And then of course, I don't have a limit switch. You may have a limit switch somewhere on the, tell you what here, you might have a limit switch somewhere in the middle of this, and those limit switches might be breaking the 24 volt side of your contactor or the common side. Either way, it doesn't matter, you're achieving the same. I'm going to go ahead and write limit switch on this, so we obviously know what that is. We're saying that this is, get a little bit bigger marker so you can see here, this is the limit switch. All right. Now we'll go ahead and finish running power to our fusible links, and we'll run power out of our contactor to the other side of our heat strips. And I'm trying to draw around the limit switch here so you can see that, let me move it up a little bit. I'm trying to keep it more center of the plate so I can get a good measurement of heat. A lot of times these contactors are not on the plates, they're over here, and the limit switch will be in the center. And they'll do that because they're like, hey, with one limit switch, then I can read that 165 degrees and open up, whether it's the top side or the bottom side. Now in the situation here, we're going to go ahead and take our low voltage, we're going to use purple for W2, and we're going to go ahead and wire it up with common, and then we're going to take our W2, and we're going to run W2 into the limit switch, providing the limit switch is closed. It'll come out of the limit switch and land on the other side of our contactor coil. And so if it's too hot, the contactor will drop out. Now, again, if the contactor sticks, I'd be surprised on a heat strip, but contactors can stick closed. Same scenario, if I wanted to protect my blower or my heat strips by making sure my blower runs, then, you know, I've got to pick a side, you know, one or two. In this situation, because there's no thermal disc, then theoretically we could just jump both sides of the contactor out. Because that's not going to change anything for ampacity reasons, but it would give us power, right, in parallel to allow our motor to run. So let's go ahead and do that real quick. We're going to go ahead and run common over to our coil side of our relay for the blower. We're going to run G over to the coil side of the relay. We're going to go ahead and take L2 and we're going to run it to the top side of the 9340. We're going to come out of terminal 3 and we're going to say that's going to run our common terminal on the motor. Now I know I have it drawn over the capacitor. Forget that. This is just an image. All right. And at this point, we're good to go. And I can take either, I'm going to use a different color here just so we're not getting too confused. I'm going to use yellow because if I use red, that might be even more confusing. But I can sit here and say, you know, the top side of this can make to the top side of that. And then at the end of the day, now I can take this terminal and run it over to the middle terminal. I apologize. I can take this terminal and run it over to terminal 3 on the 9340 relay. And what does that do? So if I don't get a call for G, right, and I get a call for W, or if I don't get a call for W and I don't get a call for G and my contactor is just stuck, or somebody just pushes in on the contactor to test out the heat strips, because some people just do that. It's not safe, but they do. And if I do that, then voltage is just going to come over, right? And it's going to energize 3. Well, as long as I have this terminal here jumped over to this terminal over here, which is terminal 4 back to terminal 3 on the relay, the 9340 relay, well, then my blower is going to run, right? And same way, as a safety going back, if I'm getting a call for G, right, and I'm not getting a call for W2, then simply I am getting one leg of power, L2 present here, which means L2 is present here. But because, you know, I'm getting a call for G, I'm normally open now on that normally closed terminal, which means I will not energize anything back up here and run my heat strips. Also, remember, if this contactor is open, then everything up here is L1, with the exception of the bottom of my contactor. So L1, 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 and L1, 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 right? All that is present. So we're not backfeeding any power. Everything's still safe. Let's see here. That's just, you know, you can go pretty far with this stuff. You know, I can add a second limit switch in there. Sometimes you see multiple limit switches. Let me erase some of this and put that up there. And we'll just go ahead and, you can always do it again. It's real easy, right? Let's see. I'm going to move this out of the way. I'm going to go ahead and shrink this down. We'll move that out of the way. We'll put this back. Again, those that use these boards know how sensitive they are and how they can not cooperate. But more experience you have with them, you learn how to get around things. Okay, so I'm going to go ahead and add another limit switch to this. All right. There we go. And we're going to go ahead and label these. limit switch, fusible link, okay? And now we'll go ahead and put our relay back in there. Enlarging this a little bit. There we go. And hopefully you can see that okay. All right. We're going to go ahead and wire it up. We're going to say L1. We're going to say L2. I'm sorry, L1 and L1 for a fusible link. We're going to come down and we're going to take L2 and wire it to the bottom of the contactor, and then we're going to come out and land the other side of the heat strip, and there we go. Very simple. Now we're going to put our 24 volts back up here. All right. We're going to go ahead and take 24 volts and we're going to land it. Yes, I am doing it differently. We're going to take our common, all right, and we're going to go in, out, in, okay? Actually make that a little bit easier for you. In, and then we're going to come out of here into the side of the contactor. So our coil now will only have a path of electricity as back to the transformer as long as these limit switches are both closed. So they are in series. So either one can drop out, and I'm using common. It doesn't matter if you use common or if you use W2. Honestly, you know, I believe it's a little easier to diagnose things using the 24 volt side of things and not the common, because common is named common for a reason, because it's common for everything. And then we're going to go ahead and wire up our low side of the 9340. We're going to come and put our G, our fan call, on the other side. We're going to come up and we're going to come off of L2, and then we're going to come out of terminal 3 and land on our common winding for our blower motor. And that's it. So if the bottom or the top limit switch opens, then I'm going to lose my path back to my transformer, and the contactor, it's not going to stay energized. If it happens to stick, okay, and my limit switches are not working in my blower, we want to make sure it's running, then simple. I'll go ahead and use a color that's not so confusing. We'll jump back over, we'll come over, we'll energize terminal 4, and then we'll come out of terminal 5, and we can come up and land on terminal 3. We don't need to repeat what that does. It's the same thing. The only thing we changed on this drawing was we put an extra limit switch in there, and instead of running W2 through it, we just ran common through all of it in a daisy chain. I think that's pretty good on this video. I'm going to do another video on adding L3, some more safeties. So if you want to watch that video, if you're confused on how 3-phase works, I'll put a 3-phase motor on there too. Again, I'm not trying to get into motors and relays so much. However, we do have to navigate our way around it a little bit on these videos. So there will be other videos that we release that specifically break down the relays and practical purposes for them. Hope this video helps out. And if you work for Ideal Conditions, you know, I know this is helping you out because I've taught the majority of you guys. If you want to get a job here one day, we're very picky on who we employ, and you're not going to be one of my service technicians unless I've taught you or one of my other instructors have taught you. But these videos are not just there for our employees as refreshers, they're also there for the entire industry. So good luck and be safe.